Hello all. So welcome back to this new lecture in the course on time series forecasting with applications in R. So again, just to give you a very quick refresher of where we stopped in the last lecture. So if you remember, we were discussing some properties of the AR1 process or the autoregressive process of order 1. And up to now, we've kind of under some assumptions, for example, constant mean and constant variance. So essentially assuming that the process is stationary, we kind of derive the variance of the AR1 process, right. So this is nothing but the variance of the AR1 process. So sigma square E divided by 1 minus phi 1 square, right. Now again in today's lecture we will kind of extend more upon such ideas. So we will try to derive the ACF function of the AR1 process and then slowly transition into moving average processes and probably random walk process. Okay. So now how would you derive the autocorrelation function of a particular AR1 process? Now again remember that why are we discussing such simpler processes is that because one can actually derive, let us say, the mean or the variance function or the ACF function of such simpler processes using a pen and paper. Otherwise one can't derive even the mean function or the variance function using a pen and paper. So one requires some software for that. But probably all these exercises would be kind of useful to understand that how to play around with, let us say, lags, or how to kind of play around with the assumptions and so on and so forth. Okay. Now again assuming that the mean is constant and equal to 0 as before. Now gamma 1, so gamma 1 means what? So gamma 1 is nothing but the covariance at lag 1. Okay. So it would be something like expectation of yt into yt minus 1. Now of course I will pause here for a second and then tell you that there should be one more term, right. I mean covariance term is what? So covariance is expectation of yt and then yt minus 1 minus expectation of yt into expectation of yt minus 1, right. So this is the exact formula for covariance, but under the assumption that both these means are 0, right. So both these means are 0. So covariance at lag 1, which is gamma 1, essentially reduces to that thing. Okay. So now what we can do is we can input the model here. So yt is what? So yt has a AR1 structure, which is nothing but phi 1 into yt minus 1 plus et into yt minus 1. Now notice here that this is a product that you have, right. So expectation of, let us say, phi 1 yt minus 1 into yt minus 1 would be nothing but phi 1 into gamma 0, because the subscripts are same, right. So if the subscripts are same, expectation of yt minus 1 into yt minus 1 is nothing but the variance, which is gamma 0, and then you have this coefficient outside, which is phi 1, and essentially as we discussed also in the last lecture, so this et and yt minus 1 are independent. So expectation of et into yt minus 1 is nothing but 0 basically. And why is that? Because we will try to explain this. So expectation of et into yt minus 1, since they are independent, I can break it down into product of individual expectations, right. So expectation of et into expectation of yt minus 1, and as per the assumption, so this is equal to 0 and again this is also equal to 0 as per the assumption. So expectation of their product is automatically 0. Okay. So further, expectation of yt minus k into et is also 0, and again using the same idea that yt minus k does not depend on et, right. So probably yt minus k depends on all the previous error terms than t minus k, right. So yt minus k is completely independent of et. So their expectation can be again broken down into individual expectations and their product, and both of them have to be zeros. Now again why do we require this assumption? So you will slowly see, which is coming in the next equation. So similarly I can actually derive gamma k. So gamma k means what? So gamma k is nothing but the autocovariance at lag k, okay, which is nothing but expectation of yt into yt minus k. Now again if you replace the AR1 structure in place of yt, which is nothing but that, so phi 1 into yt minus 1 plus et multiplied by yt minus k. Now again notice one thing here, that if you open the brackets and then take the product here, it will be expectation of phi 1 into yt minus 1 into yt minus k. So phi 1 comes outside, and expectation of yt minus 1 into yt minus k as per the notation is nothing but gamma k minus 1, because if you notice the lag, so lag between t minus 1 and t minus k is nothing but k minus 1. So I can actually write down gamma k minus 1 into phi 1, and using the above property, expectation of Et into Yt minus k happens to be 0. Alright. Now if you notice this, something interesting should happen here. So I can actually do this recursively. So how exactly recursively? So phi 1 into gamma k minus 1. Now what I can do is I can expand gamma k minus 1, right. So gamma k minus 1 will be nothing but a function of gamma k minus 2, and similarly for all the future lags. So gamma k minus 2 would be a function of gamma k minus 3, and so on. So essentially I can write down this is nothing but phi 1 into gamma k minus 2, which is nothing but phi 1 into phi 1 into phi 1 into gamma k minus 3, etc. And the last term would be something like phi 1 to the power k into gamma naught. Alright. So probably if you are not very confident, the small suggestion is you can actually try this out, right. So the next thing you have to do here is write down similar function for gamma k minus 1 and probably gamma k minus 2, gamma k minus 3, etc. until you get this recursive kind of a structure. Okay. So essentially speaking, this is nothing but phi 1 to the k, and now I can replace gamma 0. So gamma 0 is nothing but the variance of AR1, right. So we can use the same variance structure from the last class and replace it here. Alright. So we kind of get that gamma k for any AR1 process is nothing but phi 1 to the power k multiplied by sigma square E divided by 1 minus phi 1 square. Okay. And now once we get hold of gamma k, I can easily derive rho k, which is nothing but the ACF, right. So ACF is nothing but gamma k divided by gamma naught, which reduces to only phi 1 to the power k. Okay. So just to summarize what we have from this entire slide, we kind of manipulated a few assumptions here and there. So let's say assuming that the mean is constant and variances are constant and so on and so forth, we kind of arrive at this conclusion that the autocorrelation function of a particular AR1 process is nothing but given by phi 1 to the power k. Alright. So now what we have here is we have a simulated kind of a experiment. So we are kind of simulating from this model which is AR1 and coefficient is 0.6, right. So I think this slide just tells you the path of that time series process. So this is exactly how the AR1 process would look like as a simulation, of course, where that phi 1 happens to be. So this 0.6 is nothing but phi 1, the value of phi 1. So coefficient is 0.6. Okay. But now on this slide you will see that how does the ACF function of the same model look like. Okay. So ACF function of a stationary AR1 process where phi 1 equals 0.6, if you remember, the formula for ACF is nothing but phi 1 to the power k, where k is the lag, right. We derived this just a short while back. So if you look at this plot, it starts at lag 1. So let's say lag 1 is here somewhere. So at lag 1, which means k is 1, the ACF should be phi 1, right, and phi 1 is nothing but 0.6. So this is nothing but 0.6 here. Okay. So now if you move down the value of k, so let's say k is 2. So if k is 2, the value is nothing but phi 1 square. So phi 1 square is nothing but 0.6 square, which is nothing but 0.36. So at lag 2, if you see, the value is close to 0.36 and so on. So by the way, this plot is nothing but a correlogram or an ACF plot of a AR1 process where the coefficient phi 1 is nothing but equal to 0.6. Okay. Alright, so now we will kind of transition to the MA processes. So far we have kind of derived some properties of the autoregressive process. So now we will kind of derive the same properties for some of the basic moving average processes. Right. So again, if you recall, the general structure of an MAQ process is something like that. So what exactly is the difference here again? So difference is Yt is regressed on the past errors instead of the past values of Yt itself. Okay. So Yt happens to be nothing but C, which is nothing but the overall intercept or the constant mean, and then plus all the errors. So Et plus theta 1 Et minus 1 plus theta 2 Et minus 2, etc., up to theta q Et minus q, right. And again the same assumption. So what exactly are ETs? So ETs are nothing but random errors. So IID sequence with mean 0 and variance sigma square E. So essentially all these are the underlying parameters, right. So again, like I said, this slide is more like a revision slide just to recall the idea of a particular MAQ process. Okay. Now again further we will kind of do a similar thing as we did for the AR processes also. So let us say upon taking expectations on both sides of the MAQ process, right. So let us go back for a second. So this is the MAQ process. So what would happen if you take expectations on both sides? So expectation of YT happens to be C, so C is a constant, plus expected value of ET. Now again all the thetas are constants, so you can bring them out. So theta 1 into expectation of ET minus 1, and then last term would be theta q and then expectation of ET minus q, right. So this implies that expectation of YT would be nothing but C, right, and all these expectations are kind of zeros because they are expectations of the error terms. So as per the assumption, errors are nothing but random errors with mean 0. Okay. So essentially speaking what we have is something like this. So expectation of YT is nothing but a constant mean which is nothing but the overall intercept that we have in the model, which is C. Okay. And similarly what we can do is we can again take variances on both sides, right. So what would happen? So on the left hand side we will have variance of YT, then variance of C is 0 because C is a constant, right. So variance of any constant is 0, and then you have the actual model. So variance of ET, then in the model of MAQ we have theta 1. So if you bring out theta 1 of a variance, you have to square that. So it becomes theta 1 square variance of ET minus 1 and so on up to theta q square and then variance of ET minus q, right. And now what we can do is we can actually combine all these ideas, right. So by the way all these variances are kind of variances of error terms, and again as per the assumptions all of them are equal and equal to sigma square E. So essentially I can bring out sigma square E from each of these individual terms. So sigma square E from here, from there, etc. Okay. So overall if you see we have sigma square E term outside and a summation of the squared coefficients inside. So theta j square, j going from 0 to q. Okay. And then one small assumption is required here that theta 0 square is nothing but 1 basically, right, because j starts from 0. So theta 0 square is assumed to be 1, and then we will have theta 1 square, theta 2 square, theta 3 square up to theta q square. Hopefully this is clear. So the overall mean of any MAQ process is C, and the overall variance of any MAQ process happens to be this thing. So sigma square E into summation of theta j square, j going from 0 to q. Now again as discussed a short while back, we will kind of involve some basic processes. So we will start with MA1 process, right. So structure of MA1 process is as you see here. So YT equals C plus ET plus theta 1 ET minus 1. Okay. Now again as per the calculations we have done a short while back, so the overall mean function is C, while the variance function becomes sigma square y. As per the notation this is equal to gamma 0, which is nothing but sigma square E into 1 plus theta 1 square. Alright. Now how about the autocovariance function and then eventually the ACF function of a MA1 process, right. So for that what we can do is we can start by defining at smaller lags. So let us say gamma 1. So gamma 1 is what? So gamma 1 denotes the covariance between YT and YT minus 1. So here I can actually replace the actual MA1 model, right. So this is nothing but YT and then this is nothing but YT minus 1, right. So from the previous slide if you go back for a second, this is the MA1 structure, right. So I can actually write down YT minus 1 also, right. So YT minus 1 would be what? So YT minus 1 would be C plus ET minus 1 plus theta 1 ET minus 2, alright. So similarly you can actually replace YT and YT minus 1 here. So we'll have covariance of the product of YT and YT minus 1, okay, or essentially it should be covariance of this comma that. So YT comma YT minus 1. Now finding covariances of such a structure is kind of very easy. So what you do is you spot for similar subscripts. So wherever if you see similar subscripts, for example T minus 1 here and then T minus 1 there, then the covariance essentially reduces to variance, right. and for all the other terms where the subscripts are not the same, the covariance would be 0, because essentially you are finding out the covariance between error terms where the subscripts is not the same. So, according to the assumption of, so all the errors are IID, right. So, whenever the subscripts are not the same, for example, covariance between ET and ET minus 2. So, these are completely different error terms. So, as per the IID assumption of error terms, so errors are independent. So, such covariances happen to be 0. Okay. So, essentially you only have to focus on such subscripts which are kind of the same. So, for example, ET minus 1 and ET minus 1, etc. And in such situations the covariance is reduced to the corresponding variances. Okay. So, here the overall covariance of this structure becomes theta 1 and then sigma square E, and if you notice all the other product or all the other cross product terms would be zeros. Alright. Now, similarly can you extend this to one more lag. So, let us say gamma 2. So, gamma 2 means what? So, gamma 2 is nothing but the covariance between yt and yt minus 2. So, lag should be 2, right. Now, again I can do the same thing. So, I can replace yt here and I can replace yt minus 2 here and then talk about the covariance of yt comma yt minus 2. Right. Now, something interesting one can notice here, that you can't find the product of error terms where the subscripts are the same anywhere, right. So, essentially even if you take any product, for example, ET minus 1, ET minus 2, or ET minus 1 from here and then ET minus 3 from here, or ET and then ET minus 2 from here, right. So, all such combinations the subscripts are different. So, covariances of error terms where the subscripts are not the same happen to be 0, right. So, essentially the covariance here happens to be 0. So, thus this is a very important property. So, gamma k happens to be 0 for any lag above 1, right. So, gamma k happens to be 0 for all lags or for all k strictly bigger than 1, and when k equals 1, we have seen here that gamma k is nothing but how much? So, gamma k is nothing but theta 1 into sigma square E. Okay. So, when k is 1, this is the answer for the autocovariance, and for every other lag above 1 the autocovariance happens to be 0. Okay. So, using these two facts I can actually derive the ACF. So, ACF kind of takes a very simple form. So, whenever k is 1, right. So, by the way, ACF is rho k and then rho k is nothing but gamma k by gamma 0. Okay. So, whenever the lag is 1, right. So, if you remember how much was gamma k? So, gamma k was nothing but theta 1 into sigma square E, right. And if you remember gamma 0, so gamma 0 is nothing but the variance function of a MA1 process. So, if you go back a couple of slides, so this is exactly the variance function of a MA1 process. So, sigma square E into 1 plus theta 1 square, which is nothing but gamma 0, right. So, if you replace these two quantities in this ratio here, you will essentially get what you see here. So, gamma 0 is how much? So, gamma 0 is sigma square E into 1 plus theta 1 square. So, if you take the ratio of gamma k and gamma 0, you get what you see here. So, whenever k is 1, the ACF function is theta 1 divided by 1 plus theta 1 square, and for that matter for any other lag above 1 the ACF has to be 0 because the corresponding gamma k is 0. Alright. So, ACF function of an MA1 process is very easy. So, it takes some value which is this value at lag 1, but for all other lags above 1 the value is strictly equal to 0. So, now can you extend this to MA2 and then we will see what happens. So, for example, MA2 process takes that form, right. So, you extend one more lag. So, yt equals c plus et plus theta 1 et minus 1 plus theta 2 et minus 2. Okay. Now, the mean function happens to be c again as we saw earlier, while the variance function happens to be sigma square y, which is gamma 0, which is nothing but sigma square E into 1 plus theta 1 square plus theta 2 square. So, I can actually blindly apply the formulas which were derived earlier on the very first slide, right. So, the overall mean again becomes c and the variance function happens to be that thing. So, now how about the ACF function, right. So, for that I can again construct the different autocovariances one by one and then eventually see if we get some pattern or not, So again gamma 1. So gamma 1 is what? So gamma 1 is autocovariance at lag 1. So covariance between yt and yt minus 1. Okay. So again this entire thing is yt and then this entire thing is yt minus 1. So we want to find out covariance between yt comma yt minus 1. Okay. Now again you apply the exact same logic. So wherever you see same subscripts or similar subscripts, you combine those terms and then the corresponding covariance reduces to the variance. And for all other combination, right, so for all other combination the covariance reduces to 0. So here where exactly can you see common subscripts? So for example et minus 1, et minus 1, right, and then et minus 2 from here and then et minus 2 from here. So only 2 terms, right. So theta 1 et minus 1 comma et minus 1 reduces to something like theta 1 into variance, which is sigma square E, and then theta 2 et minus 2 and then theta 1 et minus 2 reduces to theta 1 into theta 2 and variance, which is sigma square E. So probably if you are finding it difficult, I can write it down. So there will be one term which is covariance of theta 1 et minus 1 comma et minus 1, right, and then plus covariance of the other term is which one? So theta 2 et minus 2 comma theta 1 et minus 2. Okay. So this covariance is nothing but theta 1 into the variance of et minus 1, which is sigma square E, and then this term is nothing but you multiply the coefficients. So theta 1 theta 2 and then variance of et minus 2, which is again as per the assumption sigma square E. Okay. So if you add these two terms, right, so if you add these two terms, this is exactly what you will get. Okay. Now extending this to one further lag. So let us say gamma 2. So what exactly is gamma 2? So gamma 2 is nothing but covariance between yt and then yt minus 2. So this entire thing is yt and then this entire thing is yt minus 2. So again the same logic. So wherever you see same subscripts, they kind of contribute to the variance, and if the subscripts are different, they contribute to 0. Okay. So for example here where can you spot same subscript? So let us say theta 2 et minus 2 and then et minus 2. So at the end of the day we will have covariance between theta 2 et minus 2 comma et minus 2. So this would be nothing but theta 2 into variance of et minus 2, which is sigma square E, which is exactly what you see here. Okay. And similarly if you follow the same pattern and then keep on extending the lags, let us say gamma 3, gamma 4 up to gamma k, so you will soon notice that you will not find any of the subscripts are common, right. So subscripts in the first term and the subscript in the second term would be entirely different. So what do you mean by that? So all the further gamma k's would be zeros. Okay. So all the further gamma k's after 2 would be zeros. Okay. So this is a very important statement. So just to combine whatever we have learned in this session is that the autocovariances and eventually the ACF function for a general MAQ process vanish for k which is strictly bigger than q, right. So if k happens to be let us say q plus 1 or q plus 2, so at that particular lag all these functions would be 0. So for example gamma k is let us say gamma q plus 1 or gamma q plus 2 dot dot dot. So at all lags above q for a MAQ process, the ACF functions and the autocovariances would be exactly equal to 0. So again here we have some illustrations, so some simulations kind of a thing. So let us say in the first plot what we have is a plot of ACF for a particular MA1 model where again the coefficient happens to be 0.6. So 0.6 is nothing but the value of theta 1 here. Okay. Now notice one thing, so this plot is nothing but the correlogram or the ACF plot. So if you go back a couple of slides, we have the function of ACF for MA1, right. So we derived that. So this is exactly the ACF function for MA1 process right here, and value is what? So if you again remember the value is theta 1 divided by 1 plus theta 1 square. Okay. So now again if you go back to that graph, we will see that where do you see the first spike. So obviously at lag 0 the value would be 1 always, right, because ACF function at lag 0, so gamma 0 or essentially this should be rho 0. So, rho 0 happens to be 1 because correlation between yt and yt itself, because lag is 0, it is always 1, right. And for all the further lag, for example 1, so whenever lag is 1 here, so the value was what, if you remember, value was theta 1 divided by 1 plus theta 1 square, and then this should be my rho 1, right. Now, in this experiment theta 1 is 0.6, so this value should be nothing but 0.6 divided by 1 plus 0.36, which is nothing but 0.6 divided by 1.36, which is kind of close to something like 0.44, something like that. Okay. And then here clearly we see that at lag 1 the value is 0.44, somewhere here. And similarly, if you see for all the future lags, so 2, 3, 4, 5, the value happens to be 0, right. So, we derived that, right. So, whatever we derived is kind of reflected in this ACF plot of an MA1 process, right. So, now probably in the next lecture what we will see quickly is that how to identify particular models based on several plots, particularly the ACF plot and the PACF plot. So, if someone is trying to analyze a time series data set and then practically work on that, so I think this is a very, very important exercise, that based on certain ACF plots and the PACF plots, can you kind of identify the underlying model, or can you have a kind of very strong guess as to what the underlying model could be, right. And one can actually do this for some very basic models. So, for example, here you see AR2 or MA2, right, and then the top row gives you ACF plots, the bottom row gives you the PACF plots. So, just based on these 4 plots, or just based on a collection of ACF plots and PACF plots, and by observing the patterns there, can you kind of identify that a possible model could be what, right. So, again like I said, the ACF plots and PACF plots are really important tools in model identification. Okay. So, probably in the next lecture we will kind of continue with this, and then we will kind of bring in the idea of random walk. So, random walk is kind of a very easy idea. So, probably we will discuss some simulated random walks, and then we will kind of derive some very, very basic properties of a random walk. Okay. Thank you.